All right, let's dive into a scientific mystery. This is a story that starts with a tiny spark but ends up completely changing how we see reality itself. We're talking about the dual nature of light, and what I like to call the case of the missing electrons.
So, what does it take to actually break a law of physics? Well, first, you need a law that everyone thinks is absolutely rock solid, completely settled. And by the end of the 19th century, the laws about light, they seemed about as solid as it gets. But a strange new discovery was about to put everything on trial.
So let's start with part one. Light. Was it a perfect wave?
Picture this. It's the late 1800s, and physicists are feeling pretty darn good about themselves. The case for light was closed. Done. They had shown that light could do all the classic wavy things. It could bend, it could spread out, it could even interfere with itself, just like ripples in a pond. Light was officially understood to be a continuous electromagnetic wave spreading its energy smoothly all over the place. This was settled science. Or so everyone thought.
And this is where our mystery really begins. Because the very scientist who helped prove light was a wave, Heinrich Hertz, he's the one who accidentally stumbled on the first clue that something was really, really wrong.
So Hertz is in his lab messing around with his equipment, and he notices something odd. Sparks seem to jump way more easily between two electrodes when he shined ultraviolet light on them. Later on, other scientists refined this. They found that if you shine light of a high enough frequency onto a metal plate inside a vacuum, you actually generate an electrical current.
The basic idea seems simple, right? The light wave hits the metal, dumps its energy into the electrons, and gives them a big enough kick to fly off. Easy. But when other scientists, like Philip Lenard, started digging into the details, well, the whole thing got a whole lot weirder. Okay, clue number one. Logically, you'd think a brighter light is a more powerful, more intense wave, so it should give those electrons a much bigger kick, right? They should come flying out of there with way more energy. At least, that's what the theory predicted. But that's not what happened.
The result was just baffling. Turning up the brightness did knock out more electrons, which created a bigger current. But, and this is the crazy part, it didn't make any single electron fly out any faster. Their maximum energy didn't change at all. That makes absolutely no sense in a wave world. It's like a giant tsunami hitting the beach, but only moving the grains of sand just as much as a tiny ripple would.
So if brightness doesn't change the electron's energy, what does? Well, the investigators decided to try changing the light's color, which is really just a fancy way of saying they changed its frequency. And this gave them clue number two. It turns out, using higher frequency light, like blue or UV light, gave the electrons a huge kick. They flew out with way more energy. But if the light's frequency was too low, say you used red light, nothing happened. Not a single electron budged. No matter how bright you made that red light, it was all or nothing. Okay, let's recap the clues, detective style, because these were completely stumping the wave theory. 1. The whole thing was instantaneous. The second the light hit, electrons were out. No delay. 2. There was a minimum threshold frequency. If your light was below that cutoff, you got nothing. 3. The brightness of the light only changed how many electrons you got, not how much energy they had. And 4. The light's frequency, its color, was the only thing that determined the maximum energy of those escaping electrons. So faced with all this weird evidence, the scientific community had to put its most cherished theory, the wave theory of light, on the stand. And let me tell you, it did not hold up well under questioning.
Let's just look at the total breakdown. The wave theory predicted that a more intense wave should deliver more energy, but the experiment? It showed intensity had zero effect on electron energy. The theory predicted any frequency of light should work, as long as it was bright enough, but the experiment showed a hard cutoff, that threshold frequency. And finally, the wave theory suggested an electron would need some time to soak up enough energy from a wave, maybe seconds or even hours. But the experiment? It was instantaneous.
The verdict was in, and it was brutal. The wave theory, which had been so successful for so long, was completely and totally unable to explain this mystery. Physics was broken.
And then, in 1905, from the most unlikely of places, a young patent clerk in Switzerland comes along and proposes a solution. An idea so radical, so completely out there, it would change science forever.
Of course, we're talking about Albert Einstein. And in one of his legendary papers from his miracle year, he didn't just try to patch up the old theory. Nope, he threw it out the window and started fresh with a breathtakingly simple new idea.
He said, what if light isn't a continuous wave at all? What if it's actually made of tiny individual packets of energy, like little bullets of light? He called these packets quanta. Today, we call them photons. And here's the kicker. The energy of each and every photon is determined by just one thing, its frequency.
And from that one idea, he came up with this beautiful, simple equation. It basically says the energy the electron flies off with is just the energy of the photon that came in minus a small phi. Think of that phi, called the work function, as the cover charge an electron has to pay to get out of the club. You know, the metal surface.
And just like that, the whole mystery completely unravels. If you think of light as these little particles, everything makes perfect sense. One photon hits one electron, it's a direct one-on-one collision, which is why it's instantaneous. If that photon doesn't have enough energy to pay the cover charge, the electron goes nowhere. That's your threshold frequency. Making the light brighter? That just means you're firing more photons per second, which knocks out more electrons but doesn't change the energy of any single hit. And finally, a higher frequency means a higher energy photon, which gives the electron a bigger kick. Case closed. Every single clue was explained perfectly.
Einstein's theory was a massive triumph. In fact, this is what he won his Nobel Prize for. But the story doesn't end here. Oh no. Solving this mystery leads to a final, mind-bending twist.
The unavoidable conclusion was that light is, well, it's weird. It's both. It behaves like a wave when it's just traveling through space, but it acts like a particle when it smacks into something. This bizarre idea is called wave-particle duality, and it just begged an even bigger question.
You see, in 1924, a physicist named Louis de Broglie had this beautifully symmetric thought. He basically said, hey, wait a minute, if waves can act like particles, couldn't particles, like electrons, protons, all the stuff we're made of, also act like waves?
And that is the ultimate takeaway from all of this. The photoelectric effect wasn't just some quirky little puzzle. It was the crack that broke reality as we knew it. It showed us that the universe is so much stranger than we ever imagined, and that the solid line we draw between a thing and a vibration, it doesn't really exist. Which leaves us with one final, deeply unsettling question to ponder. If waves of light can act like particles, and particles like electrons can act like waves, what does that make us?